All right, welcome, grade eights. Long time no talk, other than a little bit through Google Classroom. Welcome to your first virtual lesson. We're currently in the mechanical systems unit in grade 8 science. We've wrapped up light and optics, and so you already have watched a video yesterday. You might have chosen a 6-minute one. You might have chosen a half-hour one. And we're going to continue on with that. I'm going to have a little PowerPoint slide. We're going to do a little bit of calculations. You will have more time on this tomorrow. What I'm hoping is that we cover about half the slides, about a 50-slide lecture. So we're only going to cover about half in this video here today, and then we're going to cover the other half tomorrow and have you do some practice problems then, okay? So today we're talking about work in simple machines. What we see here is that we have three things here. We have a crowbar, we have a gear, and we have a screw. We're going to talk a little bit more about this in detail as we go along here. But to begin, what is work? In science, the word work has a different meaning than you may be familiar with. Most of us think work, we probably think, oh, well, like I have to apply myself to this. Well, it's kind of similar, but kind of different. So the scientific definition of work is using a force to move an object a distance when both the force and the motion of the object are in the same direction. All right. So work or not? According to the scientific definition, what is work and what is not? So the first example here is we have a teacher lecturing to her class, could be his class, their class, whoever. Our other example is a mouse pushing a piece of cheese with its nose across the floor. So what is work and what is not work? Let's go back to our definition. Using a force to move an object a distance when both the force and the motion of the object are in the same direction. Is the teacher lecturing to her class using a force? I wouldn't say so. But let's think about a mouse pushing a piece of cheese with its nose across the floor. Is it using a force and pushing on an object in the same direction? Yes, it is. So the mouse is doing work on the cheese. We go here. Now it says this is red, this is green. Colors aren't the ones I would choose, but the mouse is doing work. So the mouse is using a force to move the cheese a distance. Both the force, we got too many bars here. I'm kind of getting overwhelmed here. I will move this one maybe to up here, and then, don't like that so much. Both the force and the motion are in the same direction. All right. What's work? A scientist delivers a speech to an audience of his peers or their peers. A bodybuilder lifts 350 pounds above their head. A mother carries her baby from room to room. A father pushes a baby in a carriage. A woman carries a 20-kilogram grocery bag to her car. I want you to take a moment, think about those. Which ones are work, which ones are not? Please pause the video and then return when you are ready. So a scientist delivering speech to an audience of peers, is that work? No, there's no work being done. A bodybuilder lifting 350 pounds above their head, yes, work is being done. Now the mother carrying her baby from room to room. Now is the mother pushing the baby? No, the mother is not. So the work is not being done. It is essentially one object. Now this next one though, a father pushes a baby in a carriage. Yes, the father is pushing the baby in the carriage. And then a woman carries a 20-kilogram grocery bag to her car. Well, it shouldn't be 20 kilometers. It should be 20 kilograms. But in this one here, the mother carrying her baby and the grocery bag, both very similar in which it's being carried. It's not being pushed in a direction. So work can actually be calculated. We have a formula. We've talked about formulas. We've looked at density. I believe there's one other one we talked about. But we're going to talk about work here. And work is a force times a distance. So the unit of force is in newtons. I think we've talked about newtons before. We talked about this with pressure. And the unit of distance is meters. So distance is meters. We've done that a lot and commonly with math. Newtons we talked about. It is a kilogram meter squared. But we like to abbreviate that into newtons. It's just an easier unit for us to work with. So the unit of work is newton meters. And 1 newton meter is equal to 1 joule. So the unit of work is a joule. A unit is essentially a unit of energy. All right. And work is FD. Work equals force times distance. So calculate. If a man pushes a concrete block 10 meters with a force of 20 newtons, how much work has he done? All right, I am going to hop out of my slideshow here, and let's see if I can do this here. So we said that my distance is 10 meters. So distance is a little hard writing on the computer. Distance is 10 meters. I believe they said force is 20 newtons. It's a little messy. 20 newtons. Just like how we've done other questions, we want to make sure that we are writing down all our variables and then working from there. So we have our newtons with force. We have our distance, and we will hop back to our smart notes, and we will go in here and say work equals force times distance. If you can please pause the video, try this on your own. If you're not sure what to do next though, please follow along and stay with me here. So work equals, what's my value for force? If you said 20 newtons, you would be correct. That's my value for force. And then what is my value for distance? It would be 10 meters. Don't reach for the calculator. Do not reach for the calculator. All right. 20 times 10. What's 20 times 5? 20 times 5 is 100. Multiply that by 2. It is going to be 200. So this is 200 Newton meters. Going back to our notes on the slide, we said a Newton meter is actually a joule. So this will be 200 joules. That's how we would write our answer there. I am going to pull out my fun pens, which are my creative pens. We'll do some smiley faces since it makes us happy. And that is our work. Okay. Hop back to my slide here. Present. And let's keep rolling here. Like I said, I want to cover about half these slides in this video, and then you can watch the other half of the video tomorrow. If you'd like to go over all the slides, they will be posted today. All right. That looks like the answer we got. Awesome. Let's keep rolling. We're going to talk about power. Power is the rate at which work is done. Power is equal to work over time. So again, work is force times distance over time. The unit of power is the watt. Not like Harry Potter, where I'm a wizard, Harry. What? It's a watt. So this is our unit of power. Okay. Let's check for understanding. Two physics students, Ben and Bonnie, are in the weightlifting room. Bonnie lifts the 50-kilogram barbell over her head, approximately 0.60 meters, 10 times in 1 minute. Ben lifts the 50-kilogram barbell the same distance over his head in 10 times in 60 seconds. I have a few questions here. Which student does the most work? Which student delivers the most power? And explain your answers. All right. The only way we could calculate this is doing some calculations. So Ben and Bonnie do the same amount of work. They apply the same force to lift the same barbell the same distance above their heads. So again, they have a 50-kilogram barbell, 50-kilogram barbell, 10 times, 10 times. However, though, yet Ben is the most powerful since he does the same work in less time. Power and time are inversely proportional. And we can set in our formula here, they are inversely proportional, power and time, because power is over the 1, time would be under the work. Question 2, how much power will it take to move a 10-kilogram mass at an acceleration of 2 meters per second, a distance of 10 meters in 5 seconds? This problem requires you to use the formulas for force, work, and power all in the correct order. So it gives us formula for mass, which is mass times acceleration. We have a formula for work, which is force times distance. And we have a formula for power, which is work over time. What I'm going to do is I'm going to hop out this screen here, and we're going to take this, we're going to copy, and we're going to go back to our smart notes. I'm going to scroll down, extend, and we're going to go grab my cursor, move this, go here, paste. There is our question. So how much power will it take? Well, we have our formula for work, we have a formula for power, and we need to find our force. That's our first place to start. So our force is mass times acceleration. So I don't want that pen anymore. It's not working. Okay. Force is my mass. Let's just go down below here. Make sure I'll just do it up top here. My mass is here. My 10 kilogram mass is 10 kilograms. My acceleration is 2 meters per second, so 10 kilograms. Acceleration is 2 meters per second. And then I'll just do it underneath here. Time, or that's not time, sorry. That is a distance. I need to make sure I have that right. A distance of 10 meters. And then my time is next, which is 5 seconds. So T is 5 seconds. If you like, you always feel free to skip these parts here, me just writing this out, just so we have the facts that we need to solve the problem. So this problem requires you to use the formulas for force, work, and power on the correct order. Now, we're going to work to find our force first. So force is mass times acceleration. My mass is going to be 10 kilograms, like so. And my acceleration, we'll use an X here, is 2 meters per second. All right, 10 times 20. Force is, oh man, I feel like I'm really messy here. This is 20, and my unit for force is kilograms per meters per second squared. So this will be 20 newtons. Oops. And got a little long there. Now, what do I have to find next? What are we looking for again here? We're looking for power. Well, power is next listed here, but I need force and a distance to find my work to even get power down here. So I need to find my work next. So I'm going to switch my pen color just so we can follow along with our steps. We'll do force is in black. We'll do work in blue, and then we will do power in green here. All right, we're looking at work. Work is force times distance. So force, what is my force again? 20 newtons, yep. Put this in brackets to multiply. And then my distance is where? Here, right. My distance is 10 meters. Ka-chow. And work, oops, don't like that W. Didn't turn out nice. I'm going to undo. Not doing good with my W's here. W. There we go. That'll work. 20 times 10. We've seen that calculation before. This is, oh boy, 200 joules. 200 joules. Now that I have joules, that value will go down into there. Just like how force we could use here. And then my last step is power. Power is work over time. And my work is what? Right, 200 joules. 200 joules, like so. My time is 5 seconds. What is my value for power? It is 40 watt. 40 watt. 40 watts. There we go. All right, that is how we solve that problem there. If we go back to our slide here, we're gonna hit present. And look at that, we got 40 watts. All our calculations were done just like they had there. We're set to roll. I like to work with my units when I'm doing these calculations, just so that way I can understand where my units are coming from. All right, the history of work. Before engines and motors were invented, people had to do things like lifting or pushing heavy loads by hand. Using an animal could help, but what they really needed were some clever ways to make work easier or faster. So much think about what we did yesterday. What are some ways that would make this sort of work easier? Simple machines, let's go. Ancient people invented simple machines that would help them overcome resistive forces and allow them to do the desired work against those forces. All right, let's start with this image on the left here. What is this image of? Pyramids. Where are the pyramids located? Egypt. And then what do we have here? This would be Stonehenge. All right, let's keep rolling here. So simple machines, you would have watched those videos yesterday, and the 6 simple machines are a lever, a wheel and axle, a pulley, an inclined plane, a wedge, or a screw. Simple machines. A machine is a device that helps make work easier to perform by accomplishing one or more of the following functions: transferring a force from one place to another, changing the direction of a force, increasing the magnitude of a force, or increasing the distance or speed of a force. All right. Those are the ways that make work easier to perform by accomplishing one of the more following functions. All right. So now we're going to talk about mechanical advantage. It is useful to think about a machine in terms of the input force, the force you apply, and the output force, the force which is applied to the task. When a machine takes a small input force and increases the magnitude of the output force, a mechanical advantage has been produced. Mechanical advantage is the ratio of output force divided by input force. If the output force is bigger than the input force, a machine has a mechanical advantage greater than 1. And if a machine increases an input force of 10 pounds to an output force of 100 pounds, the machine has a mechanical advantage, MA, which is short for mechanical advantage, of 10. So 10 pounds input to 100 pounds output. Right? In machines that increase distance instead of force, the mechanical advantage is the ratio of the output distance and input distance. So formula here for us to know, mechanical advantage is equal to output over input. No machine can increase both the magnitude and the distance of a force at the same time. We're going to start with the lever. You watched those videos yesterday, so you should be an expert already in this. But we're going to go over this review. Again, this is a video, so feel free. If you're like, Mr. Wallace, I already know this, I'm going to skip a little ahead. Feel free to do that, okay? A lever is a rigid bar that rotates around a fixed point called the fulcrum. The bar may be either straight or curved. In use, a lever has both an effort or applied force and a load, which is a resistant force. All right. We have 3 classes of levers. The class of a lever is determined by the location of the effort force and the load relative to the fulcrum. Again, 6 simple machines: lever, wheel, axle, pulley, inclined plane, wedge, screw. So we have 3 types of levers here. So we have the first class lever, we have our second class lever, and we have our third class lever. Take a look. I want you to take a look and go back, or you don't have to go back, to find the mechanical advantage of a lever. Divide the output force by the input force, or divide the length of the resistance arm by the length of the effort arm. All right, so we have our resistance arm and we have our effort arm. All right, take a look over those diagrams, kind of see what's going on. All right. In a first class lever, the fulcrum is located at some point between the effort and resistance forces. Common examples of first class levers include crowbars, scissors, pliers, tin snips, and seesaws. A first class lever always changes the direction of force, i.e. a downward effort force on the lever results in an upward movement of the resistance force. So we see that here, the effort's being put here, the resistance force is going up. All right, skip that. Fulcrum is between the effort and RF, which is load. The effort moves farther than resistance, multiplies our effort, and changes its direction. All right, we're about halfway through here. I'm going to stop this screencast here. Like I said, the second part will be posted tomorrow. I don't want to overwhelm you with too much. The slideshow will be posted as well. We've only got up to slide 29 here, so we will stop here and we will continue on tomorrow. Thanks for coming and viewing this. If you have any questions, please do ask them in the classroom. Send me an email at joshua.wallace@askmu.org, or you can always contact me at the school as I'm here. Again, email is the best way to reach me. Stay safe, and we will talk to you tomorrow.